In Chapter 5, we're going to look at systems of equations and inequalities. We're going to cover 4 sections in Chapter 5. Section 1, systems of linear equations in 2 variables. Section 2, systems of linear equations in 3 variables. Section 4, systems of nonlinear equations in 2 variables. And then Section 5, systems of inequalities. In Section 1, systems of linear equations in 2 variables, we will decide whether an ordered pair is the solution of a linear system. We'll solve linear systems by substitution. We'll solve linear systems by addition. Then we'll identify systems that do not have exactly one ordered pair solution. And then we'll solve problems using systems of linear equations. A brief description of what we mean by a system of linear equations in 2 variables. Researchers identified college students who generally were procrastinators or non-procrastinators. The students were asked to report throughout the semester how many symptoms of physical illness they had experienced. The figure shows that by late in the semester, all students experienced increases in symptoms. Early in the semester, procrastinators reported fewer symptoms, but late in the semester, as work came due, they reported more symptoms than their non-procrastinating peers. The data in this figure can be analyzed using a pair of linear models. Each one of those examples, the procrastinators and the non-procrastinators, are lines. The figure shows that by week 6, both groups reported the same number of symptoms of illness, an average of approximately 3.5 symptoms per group. In this section, we will learn 2 algebraic methods called substitution and addition that will reinforce this graphic observation and will verify that 6, 3.5 is the point of intersection. So, systems of linear equations and their solutions. All equations in the form ax plus by equals c are straight lines when graphed. 2 such equations are called a system of linear equations or a linear system. A solution to a system of linear equations in 2 variables is an ordered pair that satisfies both equations in the system. A linear system that has at least one solution is called a consistent system. A linear equation with no solution is called an inconsistent system. So consistent means it has at least one solution. If there is no solution to the system of equations, that system is called inconsistent. All right, how do we determine if an ordered pair is a solution to a system of linear equations? So let's consider this system. We have 2 linear equations. The first equation is 2x minus 3y equals -4. The second equation is 2x plus y equals 4. So it's a system of linear equations. Both equations represent lines if you were to graph them, and it's a system because we have 2 of them. Determine if the ordered pair 1, 2 is a solution of the system. So how do we do this? Well, as you recall, an ordered pair is called an input-output pair. Where the first number in the ordered pair is the input, we use the variable x to represent the input. The second number in the ordered pair is the output. We use y to represent the output. So our ordered pair 1, 2, x is equal to 1, and y is equal to 2. So I'm going to make this substitution into both equations. If the ordered pair satisfies both equations, then it is a solution to that system. So we're going to replace in the first equation x, we're going to replace x for 1, or 1 for x, and 2 for y. And we're going to see if we get negative 4. So we're going to replace x with 1 and y with 2, and let's see if we get negative 4. So 2 times 1 is 2, minus 3 times 2 is 6, and that is equal to negative 4. So it satisfies the first equation, but I must check it in the second equation also. So we're going to replace the x with 1 and the y with 2. Do I get 4? 2 times 1 is 2. 2 plus 2 is equal to 4. So 1, 2 is a solution to this system of equations because it satisfies both equations. All right, is 7, 6 a solution of this system? We do exactly the same thing. We replace x with the number 7 and y with the number 6 and see if it satisfies both equations. So let's try the first equation. I replace x with a 7 and y with 6. Do I get negative 4? Well, 2 times 7 is 14. 3 times 6 is 18. 14 minus 18 is negative 4. So it satisfies the first equation. But for it to be a solution, it must also satisfy the second equation. So let's find out if it does. And 20 does not equal 4. So 7, 6 is not a solution to this system of equations. All right, how do we solve linear systems of equations? The first method we're going to look at is substitution. Number 1, solve either of the equations for one variable in terms of the other. In other words, take either one of your equations and solve it for x or for y. If one of the equations is already in this form, you can skip this step. 2, substitute the expression found in step 1 into the other equation. This will result in an equation in one variable. Solve that equation. 4, back substitute the value you found in step 3 into one of the original equations. Simplify and find the value of the remaining variable. Step 5, check your solution. You're solving equations. Anytime you solve an equation in algebra, you may check your solution to determine if you're correct. Now, where this method works particularly well is when you have a coefficient of 1 on x or y in one of your equations. That makes x or y quite easy to solve for. Where it doesn't work particularly well is when you do not have a coefficient of 1 on x or y in either one of your equations. Then you're going to have to deal with fractions. So If you don't have a coefficient of 1 on x or y, you're going to use a different method. All right, so let's solve a system of equations using this method. I'm having issues with my mirroring, so I'm going to try it over again. Here we go. So solve this method by substitution. Again, if one of your equations has a coefficient of 1 on your variable x or your variable y, this method works quite well because it's easy to solve for that variable. So in this example, the second equation, the coefficient on the variable y is the number 1. So the easiest thing to do here is to solve for y in the second equation. To solve for y, I'm going to get the 2x on the right-hand side of the equation, and I'm going to do that by subtracting it from both sides. So I get 1 minus 2x is equal to y. Now I'm going to take that value for y, and I'm going to substitute it into the other equation. My other equation is 3x plus 2y equals 4. So I'm going to take this value for y, and I'm going to substitute it in to the second equation. So I get 3x plus 2 times 1 minus 2x equals 4. And now I have an equation in one variable, x, and I can solve that equation for x. To solve this equation in one variable, I first must remove the parentheses. And I'm going to do that by distributing the 2 across. 2 times 1 is 2. 2 times minus 2x is minus 4x. I'm then going to combine like terms if I can. I have a 3x and a minus 4x. 3 minus 4 is minus 1. So I have minus 1x plus 2 equals 4. To solve for x, I'm going to subtract 2 from both sides of this equation. I get minus 1x is equal to 2. And then to find x, I need to divide both sides by negative 1. And I get x is negative 2. So the first component of the solution, ordered pair solution of my system is x equals negative 2. To determine y, I'm going to replace the x in the equation that I solved for y with negative 2, and I'm going to simplify that. So when I solve for y, I got y equals 1 minus 2x. I'm going to substitute the negative 2 in for x right there. And I get negative 2 times negative 2 is positive 4. So I get 1 plus 4 is 5. So the solution to this system of equations is the ordered pair negative 2, 5. Well, it's my proposed solution. I'm going to write it up here above my system. Now I'm going to do a quick check to make sure that it satisfies both equations. If I replace x and y with negative 2 and 5 in the first equation, I get negative 6 plus 10, and that is equal to 4. If I replace x and y with negative 2 and 5 in the second equation, I get negative 4 plus 5, and that is equal to 1. So this is the solution to this system of equations. Addition. Solving linear systems by addition. If necessary, rewrite both equations in the form ax plus by equals c. So you want x and y on the left-hand side of your equation and a constant on the right-hand side. And this constant can be any real number. Step 2, if necessary, multiply either equation or both equations by an appropriate non-zero number, so that the sum of the x coefficients or the sum of the y coefficients is 0. So what you're trying to do here is you're trying to multiply one or both equations by a constant so that when you add the two equations together, either the x's add to 0 or the y's add to 0. And then you're going to have, in step 4, an equation in one variable. So you're going to multiply by some non-zero constant so that you get opposites for the x coefficients or opposites for the y coefficients. You're going to add the two equations, that's step 3. And then you're going to solve the equation you get in one variable. Then you're going to back substitute to find the other variable and check your solution. So how does this method work? Again, I'm having issues with my mirroring, so let me try that again. Here we go. So this is the example we're going to do. We have the system of equations 4x plus 5y equals 3 and 2x minus 3y equals 7. Now I could certainly solve this system using substitution. However, since I have no coefficients on my x or y that is equal to the number 1, I'm going to be solving equations and getting fractions, and that makes things kind of difficult. So if we use the addition method, we're going to multiply one or both of the equations by non-zero constants so that we make the coefficients on either x or y opposites of each other. For example, in the first equation, I have 4x. In the second equation, I have 2x. So if I were to multiply both sides of the second equation by -2, what would happen? Let's try that. So I'm going to multiply equation 2 by both sides by -2. So I'm going to multiply the left-hand side by -2 and the right-hand side by -2. So what happens? I'm going to distribute the -2 across. -2 times 2 is -4. -2 times -3 is +6. -2 times 7 is -14. Now let's write down our first equation. 4x plus 5y equals 3. What happens if I add those two equations together? Now, since I multiplied the second equation by -2, I made the coefficient on the x -4, which is the opposite of the coefficient in the first equation, +4. So if I add these two equations together, the x terms add to 0, so they disappear. And I'm left with an equation only in y. So I have 6y plus 5y is 11y. -14 plus 3 is -11. Divide both sides by 11, and I get y is -1. So I have the second coordinate of the ordered pair that's the solution to this system of equations. Now to find the value for x, I can substitute -1 in for y in either one of the equations. It doesn't matter. So I'm going to back substitute -1 for y in either equation 1 or equation 2. I'm going to choose 1. So I'm going to replace the y with -1. Five times -1 is -5. I'm going to add 5 to both sides. 3 plus 5 is 8. And divide both sides by 4, and I get x is 2. So the ordered pair that I propose as a solution to this system of equations is the ordered pair 2, -1. And I am going to do a quick check to make sure that works. If I replace x with 2 and y with -1 in the first equation, I would get 8 minus 5, and that is 3. If I replace the x with 2 and the y with -1 in the second equation, I get 4 plus 3, and that is equal to 7. All right, so from our procrastinator, not procrastinator example earlier in this section, we saw that when we had two lines that intersect each other, they intersect at an ordered pair. So when you have a system of two linear equations, if they intersect, that means you have a solution and it is an ordered pair solution. So if you have exactly one ordered pair solution, that means the two lines intersect at a point, at one point. If you have a system of equations and you have no solution to that system of equations, that means the two lines are actually parallel to each other. Parallel lines never intersect. They never touch. So if you have two lines that never intersect, they're never going to intersect at an ordered pair. So the system of equations with those two equations will not have a solution. Now, the third case here is when you actually have the same line. When the two lines are identical, if you have just one line, how many ordered pairs are there on one line? Well, there are an infinite number of ordered pairs on a line. So if your system is actually, the two equations are exactly the same line, then you have an infinite number of solutions. So let's show you what happens when you have one of these two special cases. So the first system we're going to look at is a system with no solution. So these two lines are actually parallel to each other. So what happens when you try to solve a system of equations and that there is no solution? All right, so I'm going to solve the system 5x minus 2y equals 4 and minus 10x plus 4y equals 7. Now, I would probably multiply the first equation by the constant 2. That's going to make the coefficient on my x 10x. And then when I add that to the second equation, whose coefficient on the x is minus 10, I'm going to get 0 for the x's. So I'm going to do that. I'm going to multiply the first equation by 2, both sides. Okay, so I get 10x minus 4y equals 8. Now I'm going to add that to the second equation to eliminate the x's. But what happens here? 10 minus 10 is 0. But look at what happens with the y's. I have minus 4y plus 4y. That is also equal to 0. So the left-hand side of my equation is the number 0. However, the right-hand side, 8 plus 7 is 15. All right, this is not true. 0 does not equal 15. So when you're solving a system of equations and you get a statement that is not true, it's false, that means this system does not have a solution. So what I obtained here is false. 0 does not equal 15. Since that statement is false, this system has no solution. And a system that does not have a solution we call inconsistent. If you were to graph these two lines, you would find that these two lines are parallel. And two lines that are parallel never intersect. So this system will not have a solution. You can also say that the solution of this set is the empty set. The empty set is that set that doesn't contain any elements. So again, we say that there is no solution, or the solution is the set that's empty, the empty set. We also say that the system is inconsistent. All right, what happens when we have a system with infinitely many solutions? So let's look at this system. We have x equals 4y minus 8 and 5x minus 20y equals negative 40. So I would think that substitution would be a good method to use to solve this system, because the first equation is already solved for x. So I'm going to replace the x in my second equation with the 4y minus 8. So I'm going to substitute 4y minus 8 in for x in that second equation. All right, so I'm going to distribute the 5 across. I get 20y minus 40 minus 20y equals negative 40. And look what happens on the left-hand side of this equation. When I combine my terms, I get 20y minus 20y, that's 0. So what I have left on the left-hand side of this equation is negative 40. And that's true. Negative 40 is equal to negative 40. All right, so when something like this happens, there are actually infinitely many solutions. And if I could spell infinitely many solutions. So what this means is these are actually the same line. And any ordered pair that's on this line is a solution to this system of equations. So the way you could write this, if you wanted to, is you could say that it's a set of any ordered pair xy such that x is 4y minus 8. So any ordered pair that satisfies that equation is a solution to this system, because they're exactly the same line. X equals 4y minus 8 and 5x minus 20y equals negative 40. If you were to solve the second equation for x, you get exactly the same thing as the first equation. They're exactly the same equation. And since they're the same equation, any ordered pair that is on that line is a solution to that system. And you can see on this slide, I wrote the solution this way. You could also write the solution using the second equation. They're exactly the same equation. So you could say it's the set of all ordered pairs xy such that 5x minus 20y equals negative 40. Both of those are correct. All right, let's solve a break-even point problem. A company that manufactures running shoes has a fixed cost. We've been doing this all semester. Fixed cost, variable cost. Has a fixed cost of $300,000. Additionally, it costs $30 to produce each pair of shoes. They are sold at $80 a pair. Write the cost function of producing X pairs of running shoes. Write the revenue function, R, from the sale of X pairs of running shoes. So what would the cost be? Just like all semester. The cost function is going to be your fixed cost plus whatever your variable cost is. So my cost is going to be my fixed cost plus it costs me $30 to manufacture each pair of shoes. And if X is the number of shoes I manufacture, then it's going to cost me 30X per shoe. Okay? Now my revenue, I'm going to sell these things for $80 a pair. So my revenue for each pair I sell, I'm going to bring in $80. So my revenue is going to be 80X. All right, what's break even? Well, where you break even is when your profit is zero. Okay, where is your profit equal to zero? Well, your profit's equal to zero when your cost and your revenue are the same thing. So when cost equals revenue, your profit's zero. If your revenue is larger than your cost, then you're going to make a profit. If your revenue is smaller than your cost, then you're not making a profit, you're losing money. So when my revenue equals my cost, then I'm breaking even. So we're going to set these two equations equal to each other and solve for X. So my cost function was 300,000 plus 30X, and my revenue was 80X, and we're going to set those two equations equal to each other. I'm going to subtract 30X from both sides. I get 300,000 equals 50X. Divide both sides by 50. And I get X 300,000 divided by 50, I get 6,000. So my break-even point, if I manufacture 6,000 pairs of shoes, I'm going to break even. All right, so how much revenue cost is it going to be at 6,000 pairs of shoes? So I can determine the cost or the revenue, they're going to be the same number, by substituting 6,000 back into either equation. And it doesn't matter which one you substitute into because it's going to be the same thing. Revenue and cost are the same value. So I'll do the second equation because it's easier. So I'm going to find the revenue at 6,000. That's going to be 80 times 6,000. Take my handy dandy calculator out, and I get $480,000. So my break-even point is 6,480,000. I probably shouldn't put a comma in the 480,000. It makes it kind of confusing. Let's put a dollar sign in there, and that'll make more sense. All right, and that's the end of section 5.1.